So today's video is going to be about calorimetry. And calorimetry is the method by which enthalpies are determined, pretty simply. All right? So this is how the terms, the energy changes that are involved in chemical reactions or physical changes gets calculated. Now the basic thermochemical equation for calorimetry is this. Goes Q is equal to M times delta T times C. I'm going to explain every one of these. Q right here is heat. And for reasons that I'm not really going to go into, the heat Q we are going to say equals delta H. Delta H is actually a little bigger deal. Enthalpy, it's a capital letter. There's all sorts of things going on that someday you'll learn, but for right now, think of delta H and Q as being pretty much the same thing. Now, the next term is mass. The next term is change in temperature. So it's going to be T final minus T initial. And then the last factor right here is kind of an interesting one. It's called specific heat. And specific heat is sort of a correction factor because all materials have slightly different abilities to absorb energy or to store energy. It's kind of the same thing. And so you guys know this probably. If you're asked to figure out what's going to heat up quicker, a block of wood or a cast iron skillet, you would say a cast iron skillet's going to heat up quicker because a cast iron skillet has a lower specific heat. The lower the specific heat, the faster it is going to change temperature with a certain amount of heat being added to it. So to sort of explain this equation, because right now, it's just a bunch of heat is equal to the mass of something. Let's say I want to talk about the difference between temperature and heat. So let's say I have this glass of water and I have a thermometer sticking down in it. Okay? And the thermometer is reading 50 degrees Celsius. And then over here I have this huge bathtub. Well, not a huge bathtub, just like a bathtub. Okay? Little feet coming off here like that. And I put a thermometer into this bathtub, stick it in, and it's also reading, let's make that, a plus 50 degrees Celsius. You got to remember that temperature is a measure of average kinetic energy. And that's all it is. It's measuring how fast the little molecules or atoms or ions or whatever are moving around in there if I take an average. Well, just like any average, the average, I can take an average of 3 things, or I can take an average of 3 trillion things. That's what I'm doing. The average of the molecules making up this little glass of water have an average kinetic energy of 50, that's proportional to 50 degrees Celsius. The average of a lot more molecules making up this bathtub of water has an average of 50 degrees Celsius. So this kind of tells you the difference between temperature and heat. Obviously, it took a heck of a lot more heat to get the bathtub full of water up to 50 degrees than it did to get the little glass of water. So that difference is energy. All right? And energy is going to be calculated up here with this delta, with Q, which we are going to then go a little further and just say it's the enthalpy H. All right? So here's sort of how a calculation would go initially. All right? Let's say I have a glass of water right here. And in that glass of water, I am going to throw an ice cube. like this. There's an ice cube in there. And I have a thermometer sticking down in there. Now what I want to do is I want to calculate the amount, I want to calculate the heat of fusion for ice. And we already know what that is. It's 6.01 kilojoules per mole. So here's how I'm going to go about doing it. Because this heat, delta H, is really tricky to calculate. If you had an easy way to calculate calories or kilojoules in a product, you'd be very wealthy, because it is tricky to do. You can't just stick an instrument into something directly and figure out exactly what that amount of energy in there is going to be. What you need to do is you need to transfer that energy to something else, use the basic thermochemical equation, and figure it out. So here's how it's going to go. Okay? This ice cube is going to absorb heat from the water, because the water is at a higher temperature. So the ice cube, the H2O solid, is going to absorb energy. So it's going to absorb heat. And what that's going to do is it's going to turn it into H2O liquid. All right? Well, at the same time, the H2O liquid, all the water surrounding there, is going to be giving off the heat. So what happens is, as far as this process goes, the delta H, or the heat that's going to come off of that, for the H2O solid, okay, is going to be positive, and that's going to equal a negative delta H for the H2O liquid, because that's going to be exothermic. And this is not simple stuff. It's kind of complicated. But this is the process. If one thing is going to give off energy, the other thing has to absorb the energy. Well, we don't know exactly how much the ice cube is going to absorb, but what we can figure out, and this is the calorimetry part, we can figure out how much energy the water lost. And the way I'm going to do that is I'm going to use that equation that I just gave you. So let's say the water was sitting here initially at 50 degrees Celsius. And then all of a sudden it dropped down, okay, after I put the ice cube in and the ice cube melted, it dropped down to 36 degrees Celsius. The other piece of information I need to know is that I had 100 grams of water sitting in there. So now what I can do is I can say, okay, the heat that was given up by the liquid is going to be equal to the mass of the water that gave it up, 100 grams, times a change in temperature. The temperature final was 36. The initial was 50 degrees. And then times that correction factor that I talked about, the specific heat, which sort of puts everything into, allows for different packing of elements or atoms together. For water, and this is specific for water, happens to be 4.18. And the units on that are joules per gram degrees Celsius. We'll talk more about what that whole specific heat thing is, but it's a correction factor, okay? So now all I got to do is I just got to multiply that through, and I'm running out of time, so I got to make this fast. So 100 times 14 times 4.18 gives 5,852, it's negative, joules of energy. So that means, because of the calorimetry part of this, if that was given off by the water, okay, that means the amount that the heat that the ice cube absorbed was a positive 5,852 joules. All right? Well, we'll pick it up there a little bit later.